So now that we've got some hopefully new insight into the multivariate normal distribution, let's look at some of the practical issues in terms of checking whether our data might be normally distributed. So the way we do this is that we compare empirical results to our theoretical expectations. And what we talked about in the last video was the sort of theoretical idealized version of multivariate normal distribution. But what we deal with are samples, which are, we hope, often drawn from populations that are normally distributed or multivariate normally distributed. So what we want to do is compare our observations to our theoretical expectations. So as you, I believe, talked about in lecture, or will talk about in lecture, if a distribution is multivariate normal, it also means that each individual univariate distribution must be normal. This doesn't go the other way around. We can't assume just because all variables are univariate normal, that means their joint distribution is multivariate normal. But if distribution is multivariate normal, it does mean all the univariate distributions must be normal. So we're going to review univariate normality checks first. What we're going to look at here are QQ plots. I assume we've all seen QQ plots before, but maybe not really gotten into the weeds of exactly how they work. And so we're going to practice a little bit of how we can actually generate QQ plots and exactly how they work, hopefully to drive that intuition home a little bit more. And some of you may know this already, some of you may have seen this already. Let's work through it either way. And so what we're going to do is we're going to generate QQ plots by hand using R. So this is example data from the book. So in this example, we have 10 observations of univariate data. So the first thing we want to do is put them in order. So here I just load them in the same order they were originally listed in the book, or I don't know, I might have just mixed this up randomly, I can't remember. But so here's just unordered data. And so to get it in order, we can use this order function. So we index it by the order, which means we use the square brackets. So that then gives us our data in ascending order from smallest to largest. And then what we can do is we can create an index value for each observation, which I'm going to call J, just by counting the number of observations. So this is going to go from 1 to the length of the data set. You might, if you don't just have a single variable, you might use n row here instead of length, but here we just have one variable. So we see we get indexes that go from 1 to 10. So we want to obtain the corrected expected probability levels. So to do that, we use this formula J minus 1 over 2 divided by n, where J is the ordered index and n is the sample size. So we can, again, use length here to get the sample size. If we had more columns, more than one columns, we'd use n row, but when we only have one column, we use length. So here I take J minus 1 over 2 divided by length DAT. This will evaluate to 10, of course. This is just good to be in the practice of doing this to make your code reusable for or more generalizable. So this way we could run the same code again with a different variable that had a different sample size and it would still work. And so you see these are the expected probability values for 10 observations drawn from normal distribution. And so what we want to do now is find the quantiles of a normal distribution associated with these probability values, and then compare them to our actual observed data. So we can use the qnorm function for this. So what this is telling me is 1.645 is the 0.05 quantile associated with a normal distribution. And since the normal distribution is symmetrical, we're just we see that it's symmetrical on either side of 0.5. So we get negative 1.645 here in one tail, 1.645 in the other tail, 1.036, 1.036. So these are the quantiles of the normal distribution associated with these probability values. So now what we want to do is compare our observed values to our expected quantiles of standard normal distribution. And ideally, these will be highly correlated, and that's what a QQ plot does. And so we're going to skip the data argument here in ggplot. So to do that, we just go directly to mapping, which we often leave out. But here, so we're going to start with mapping equals AES. So I go ggplot mapping equals AES. So X is our quantiles. These are our theoretical normal distribution that we got here. So it's these values that are associated with our expected probability values. And then the y-axis is our observed data. And so it's just our ordered observed data. It's here. And we note that we get a nice straight looking line. Our data does appear to be following the expected normal distribution that we would, a distribution we would expect to see if our data was drawn from a normal distribution. Of course, we can check our QQ plots with lots of automatically generated plots. There's the QQ norm function. There's QQ plot in the car package, which gives you these kind of funky lines and confidence bands. You can do it in ggplot with geom_QQ, and geom_QQ line gives you the line plot. And so those are just different ways of getting automatic QQ plots. The same plot that we generated on our own here, just by estimating the expected quantiles and comparing it to our actual data. So the book also talks about a significance test. And so this is a significance test for the correlation coefficient between the observed and theoretical quantiles. So it's essentially the correlation coefficient that would be associated with this plot. That's the correlation between the theoretical and sample values. The formula for getting this correlation, it's just a standard correlation formula. It's on page 181 of your book. I'm not going to reiterate it here. And so this is a test statistic for this correlation between the theoretical and sample quantiles, and this is known as the Shapiro-Francia test. There's also a table in your book that includes test statistic values for different levels of alpha. And so here, the null hypothesis is that the data is normal. So the null hypothesis is essentially that this correlation is 1, and we would reject it if the correlation is sufficiently low given the sample size. So this test is available in the NOR-test package as half test. And so here we see the test statistic is W, the correlation is very high, so therefore the p-value is very high, and so we retain the null hypothesis that this correlation is 1. These data are drawn from a normal distribution, p greater than 0.99. It's a really high. There's a similar test, which is maybe more common. It's called the Shapiro-Wilk test. And so this can be obtained with the Shapiro test function. This is included in base R. You don't need any special packages. And the results are typically going to be very similar. We see the results are almost exactly the same to what we got here. It's off in the third digit. These are ways you can test for univariate normality. So how can we extend these principles to multivariate normality, or the multivariate normal distribution? Let's sort of think this out. Our procedures so far are based on comparing observed values to their expected theoretical position along a normal distribution. That's what we did for the univariate case. Do we have a way where we could define a similar theoretical expectation for the multivariate distribution? And this is, in fact, exactly what we spent the first video talking about. So this would be the distance that we learned about in the first video, the Mahalanobis distance. Again, I probably pronounced that wrong, I'm not sure. And so we denoted this c squared when we were talking about the theoretical population distributions in the last video. When we're talking about sample observations, we're actually going to call it d squared. And we'll call it d squared j to denote that it's a particular observation from a given sample. And so we're using xj to denote this is the row, essentially the observation that we're talking about. So this is the row in the data. So this is one observation of several different variables. And this is the the observed mean vector. So instead of mu, we have x bar. And then instead of sigma, inverse sigma, we have inverse S for our sample covariance matrix. And so here d squared is the distance of observation j along the multivariate distribution defined by our sample. And so we can recall that c squared is distributed chi-squared with p degrees of freedom. And so we can use the chi-squared distribution as our reference distribution, our theoretical distribution, and do basically the same thing we did with the standard normal distribution in the QQ plot. So we begin the same way. We get our d squared values, order them from largest to smallest, and then we're going to compare them to quantiles of the chi-squared distribution. And so we're going to do essentially the same thing. We're going to get quantiles for our chi-squared distribution defined by the same probability, j minus 1/2 divided by n. This is exactly what we saw in the univariate case. The main difference here is that we are using the chi-square distribution with p degrees of freedom, where p is the number of variables, and of course n is the sample size. And again, we can plot the relationship between d squared and our quantiles of the chi-square distribution, just like a QQ plot. One word of warning: this relationship may misbehave in cases where either the sample is small or there are a similar number of variables to sample size. So if n minus p is also small, this relationship, this chi-square distribution or expected chi-square distribution can misbehave. But we can still use a small sample to illustrate the procedure. So this is a data file that has 10 observations of 3 variables. And so we can use it to generate a chi-square plot similar to our QQ plot. So the first step is going to be to get the d squared value. So how do we do that? We use our sample mean vector and our sample covariance matrix, and we just get the quadratic form of our squared error the same way we did in the last video for the population distribution. So what do we need? We need to get our mean vector and our inverse covariance matrix. So here I'm getting the mean vector the same way we looked at in the stats video. I'm creating a vector of 1s, and then I'm transposing the data and multiplying it by the vector of 1s and dividing by the sample size. So here's our mean vector. And so for the covariance matrix, I'm not going to go through all the calculation steps here. I'm just using the COV function to get the covariance matrix, and then using the solve function to get the inverse. So now we can get our distances by computing the data minus the mean vector transposed times the covariance matrix times the data minus the mean vector. So here I'm illustrating with the first observation from the data, so the first row of the data minus the mean vector, of course transposed, times the inverse covariance matrix, again times the first row minus the mean vector. And so this is our first distance value here, 1.67. To get all 10 rows simultaneously, I can use a loop. There are probably ways to do this with a function. There's probably an apply function like mapply or something like that. I just didn't want to keep poking around and trying to figure it out. I know how to do this with a loop. So when we want to run a loop and save all of the output, when we're going to have more than one outputs, we need to initialize something, and in this case, an empty vector of 10 observations where we can save each distance. So here I'm just creating 10 missing values. So this is ds will start out as just a vector of 10 NAs. And then as I run my loop, I is the index, and I'm going to go from 1 to the sample size, which is n row DAT. So this is going to be 1 through 10. So this is just going to do the same thing we just saw for each I. So it's going to go for the first row. And so the first row, as we see here, is going to be the same result we got before. And it's going to go to the second row and get the second distance. And it's going to go through each row. And then as it goes through each row, it's going to save the result to each element. It's going to replace each NA in this DS vector that I created with the distances. And so here we see we get the distances for each observation. Of course, there's a much easier way to do this. There's the Mahalanobis function that can do it for us. We just need 3 arguments for it. We get x as the data, center equals the mean vector, and cov equals the covariance matrix. And so we can do this all a much easier way. We can get the mean vector with colmeans. We can get, of course, covariance with cov, and then enter them all into the Mahalanobis function. And we see we get the exact same result. This result here is exactly the same as what we got here. So now we can proceed to get our chi-square plot. So first we're going to put our distances in order the same way we did with our observations in the univariate case. We're going to create our index. So again, we have 10 observations, so we're going to go from 1 to 10. We're going to create our probability values. Again, it's because we have 10 observations. These are going to be exactly the same as we saw before. And then we need to get our quantiles associated from the chi-square distribution associated with these probabilities. So before this was from the normal distribution, now it's from the chi-square distribution. And so we can do this with q chi-square. We need 2 arguments. P is the probabilities. So P is these probabilities here that we just created, the expected quantiles. And then we also need degrees of freedom, which is P. So in this case, 2. We can always use ncol to define P. So this is just going to evaluate the 2 because it's the number of columns in my data set. And so we run this and we get our quantiles of the chi-square distribution. And in theory, these should be highly correlated with our d-squared values, our distances. Ideally, they'll line up along a straight line, just like the QQ plot. And so here's our result. You see this looks a little funky and curved. Again, this is going to misbehave sometimes, especially in small samples, but even this isn't too bad. Kind of looks like it's not too far off from a straight line. If it was a QQ plot, we'd be a little worried, but again, because it's a chi-square plot and it's a small sample, we're not that worried. And we can also use the heplots package. So this has an automatic chi-square plot via the CQplot function. And so we see it gives us a much nicer looking plot with a line and the confidence band. And we see all the points are lined up inside of this confidence band. So we can essentially use this as a heuristic way of evaluating this data as probably being multivariate normal. And of course, there is also a test statistic. It's called Mardius test. Mardius test can apply to either the univariate or multivariate case. So what Mardius test actually does is it tests the null hypothesis that the skewness equals 0 and that the kurtosis as the expected kurtosis. So the expected kurtosis is actually going to be p times p plus 2. And so we can see in the univariate case, this is going to be 3. So the expected kurtosis for univariate data is 3. Sometimes it's shifted by subtracting 3, so it's 0, but technically it should be 3. In the multivariate case, skewness is still 0, but kurtosis is p times p plus 2. And so Mardius test is a null hypothesis test for these outcomes. So there's a Mardia function in the psych package. It's kind of a complicated output. B1p is the estimated skewness. B2p is the estimated kurtosis. Skew, small sample skew, and kurtosis are test statistics. And then the width probability part are p-values. And the small sample skewness includes a correction that helps test the skewness when the sample size is small. And so we run it here. And so we see we get our output, we get our B1p, that's our skewness, our test statistic for our skewness, our p-value. We're actually going to use this one because it's a small sample skew. Test statistic is 5.57, p-value is 0.85. And so our estimated kurtosis is 9.63. And so the test statistic is negative 1.55. Remember, it's p times p plus 2 is the expected value for this. So this would be, we have 3 variables, so that would be 3 times 3 plus 2. So that would be 15. So this is obviously less than 15, which is why the test statistic is negative. Our p-value is low, but it's still above 0.05, above 0.10. So here we'd say using the small sample skewness test, we retain the null hypothesis that the skewness is consistent with multivariate normal, or that the skewness is 0, p equals 0.85. We retain the null hypothesis that kurtosis is p times p plus 2, or 15, p 0.12. We can also get a plot from the Mardia function. I'm not exactly sure what this plot is. It's not exactly the same as the chi-square plot that we saw, because if you note, the x-axis includes negative values. The chi-square distribution does not. So this is something similar to what we saw. It's a slightly different version of the plot. It's another version of a QQ plot for multivariate data. And so you have that as well.